You remember yesterday. You don't remember tomorrow. Simple fact. Obvious. Everyone knows this. Time flows forward. The past is fixed. The future is open. That's just how it is. But why? Most people have never actually asked this question. They accept it as obvious. Time moves forward because that's what time does. But that's not an answer. That's just naming the mystery. When you really ask why time flows in one direction, when you dig into what physically forces the universe to move from past to future and never backward, you discover something so profoundly strange that it changes everything you think you know about reality. The direction of time is not a law of physics. It's not written into the fundamental equations. It's a consequence, an accident, a statistical inevitability emerging from one fact about how the universe began. And that fact is so specific, so unexplained, so utterly mysterious that physicists still don't understand why it's true. Let me show you what I mean. Start with physics, the fundamental laws, gravity, electromagnetism, quantum mechanics. These laws govern everything. Planets orbiting stars, electrons in atoms, light traveling through space, every interaction. Now here's the strange part. These laws don't care about the direction of time. They work exactly the same forward and backward. Take a planet orbiting a star. You can run the equations forward. The planet goes around. Now run them backward. The planet still orbits, just in reverse. The equations don't break. Nothing becomes nonsensical. The backward version is just as valid as the forward version. Same with electromagnetism. A charged particle moving through a magnetic field curves in a specific direction. Run it backward. The particle curves the other way, but the laws still hold. The mathematics is identical. Even quantum mechanics, the Schrödinger equation, which describes how quantum states evolve, is time symmetric. You can run it backward, and it works perfectly. This is called time reversal symmetry. The fundamental laws of physics don't distinguish past from future. If you showed a physicist a video of fundamental particles interacting and asked whether it's running forward or backward, they couldn't tell. Both directions obey the same laws. But now look at the real world. Drop a glass. It shatters. Pieces fly everywhere. That's what happens. Always. Now imagine running that backward. Shards of glass on the floor suddenly leap up, assemble themselves perfectly, and the glass sits intact on the table. Does that ever happen? But here's the thing. Nothing in the fundamental laws of physics forbids it. If you tracked every atom in those glass shards, every air molecule, every photon, and you reversed all their velocities, the glass would reassemble. The laws allow it. The equations work backward just fine. So why doesn't it happen? Or consider a cup of hot coffee sitting on a table. Heat flows from the coffee into the air. The coffee cools down. The room warms up slightly. That's what happens. Heat flows from hot to cold, always. Now imagine the reverse. Heat flowing from the cool air into the coffee, making it hotter while the room gets cooler. Does that happen? No? But again, the fundamental laws don't forbid it. If every air molecule happened to move in just the right way, transferring energy to the coffee molecules instead of away from them, the coffee would heat up. Nothing in the equations prevents this. It's allowed. So why doesn't it happen? This is the mystery. The laws of physics are time symmetric, but reality is not. The universe moves in one direction. Glasses break but don't reassemble. Heat flows from hot to cold, not the other way. Eggs scramble but don't unscramble. Something is forcing time to have a direction, and it's not the fundamental laws. The answer is entropy. But to understand entropy, you need to understand what it actually is. And it's not what most people think. Entropy is not disorder. That's the common explanation. But it's misleading. Entropy is about probability. Here's what I mean. Take a box of gas, 100 molecules bouncing around. At any moment, those molecules have positions and velocities. That's the state of the system. Now, some states look ordered. All the molecules on one side of the box moving together. Other states look disordered. Molecules spread out randomly, moving in random directions. Here's the key. There are vastly more disordered states than ordered states. Vastly more. If you have 100 molecules and you ask how many different ways they could be arranged with all of them on the left side, there's essentially one way. They're all on the left. But if you ask how many ways they could be arranged randomly throughout the box, there are trillions upon trillions of ways. Different positions, different velocities, all looking roughly the same, randomly distributed. This is entropy, the number of microstates, the number of different arrangements that produce the same overall appearance. Ordered states have low entropy because there are few ways to arrange things to look ordered. Disordered states have high entropy because there are many, many ways to arrange things to look disordered. And here's the critical insight. If you start with a low entropy state and let the system evolve, it will almost certainly move toward higher entropy. Not because there's a law forcing it, because it's vastly more probable. If all the molecules are on the left side and you let them bounce around, they'll spread out. Why? Because there are so many more ways for them to be spread out than to stay clustered on one side. The system is exploring possible states randomly, and the overwhelming majority of those states are high entropy. It's not that some force pushes them toward disorder. It's that disorder is the default. It's where almost all the possible states are. Think of it this way. You have a deck of cards, perfectly ordered. Ace through king, all 4 suits in sequence. That's one specific arrangement. Low entropy. Now shuffle the deck. What happens? The cards get mixed up. The order disappears. Why? Because there's only one way to arrange the deck in perfect order. But there are billions of ways to arrange it randomly. When you shuffle, you're sampling from all possible arrangements, and almost all of them are disordered. You could, in principle, shuffle the deck and get it back in perfect order. The laws of card shuffling don't forbid it, but the probability is so absurdly low that it will never happen. Not in your lifetime, not in the lifetime of the universe. That's entropy. And that's why glasses don't reassemble. That's why heat flows from hot to cold. That's why eggs don't unscramble. A broken glass has high entropy. The shards can be arranged in countless ways and still look like a broken glass. An intact glass has low entropy. The atoms must be arranged in one very specific configuration to form a functional glass. If you start with a broken glass and let atoms move randomly, the probability that they'll arrange themselves into an intact glass is essentially zero. Not because it's forbidden, but because there are so many more ways to be broken than to be intact. Same with heat. Hot coffee has molecules moving fast. Cool air has molecules moving slowly. As they interact, energy gets distributed. Fast molecules slow down. Slow molecules speed up. Eventually, everything reaches the same temperature. That's high entropy. Energy evenly distributed. Could energy spontaneously concentrate back into the coffee? Yes, if by chance all the slow air molecules happen to hit the coffee at just the right angle to transfer energy inward. But the probability of this is so staggeringly low that it never happens. The universe moves from low entropy to high entropy because high entropy states are overwhelmingly more probable. That's it. No mysterious force, no fundamental law, just statistics. And this is the arrow of time. The direction time flows is the direction entropy increases. When you remember the past but not the future, you're experiencing the arrow of time. Memories are low entropy states, information stored in specific neural patterns. As time goes forward, entropy increases, disorder grows, and those patterns degrade. That's why you remember yesterday but not tomorrow. The past left low entropy traces. The future hasn't happened yet. When you see a video and know whether it's running forward or backward, you're detecting entropy. A glass shattering is entropy increasing. Run it backward, entropy decreases, and you immediately know it's reversed, because glasses don't spontaneously assemble. The entire structure of cause and effect depends on entropy. Causes come before effects because causes are low entropy events that produce higher entropy outcomes. You drop the glass, low entropy action. The glass shatters, high entropy result. You never see the reverse because the reverse requires starting from high entropy and ending in low entropy, which is statistically impossible. But here's the question that should break your brain. If the fundamental laws are time symmetric, if entropy always increases toward the future, then entropy should also increase toward the past. If you run the equations backward, entropy should still grow, but it doesn't. The past had lower entropy than now. Yesterday was more ordered than today. 1 billion years ago was even more ordered. Why? Because the universe started in an incredibly low entropy state. The Big Bang was not a chaotic explosion, it was an extraordinarily ordered event. The early universe was smooth, uniform, almost perfectly homogeneous. That's low entropy. And ever since, entropy has been increasing. The universe has been moving from that initial ordered state toward higher and higher entropy. Stars form, galaxies cluster, black holes grow, energy spreads out, disorder increases. The arrow of time exists because the universe had a beginning, and that beginning was highly ordered. This raises the deepest mystery in all of physics. Why did the universe start with low entropy? Why was the Big Bang so ordered? We don't know. There's no law that requires it. In fact, it's incredibly unlikely. A high entropy beginning would be far more probable. A chaotic random initial state makes more statistical sense. But that's not what happened. The universe began in a very specific, very low entropy configuration, and we have no idea why. Some physicists think there's a deeper explanation. Maybe our universe is part of a multiverse, and different universes have different initial conditions. We exist in a low entropy universe because only those universes allow for complexity, structure, life, observers. Others think the Big Bang itself needs a deeper theory. Maybe quantum gravity explains why the universe started ordered. Maybe there's some mechanism that sets initial conditions. But right now, we don't know. The low entropy beginning of the universe is a brute fact. It's the most important unsolved problem in cosmology. And everything about time flows from this one fact. The reason you remember the past, the reason cause precedes effect, the reason entropy increases, the reason the future feels open and the past feels fixed. All of it comes from the fact that the universe started in an improbable, highly ordered state. Here's another way to think about it. The past hasn't gone anywhere. It's still here, encoded in the present. When you see footprints in sand, you're seeing the past. The low entropy configuration of those grains encodes information about what happened. Someone walked there. The footprints are a memory, a trace of a past event preserved in the present. Same with fossils. Same with photographs. Same with your brain. Memories are physical structures, low entropy patterns that encode past states. The past isn't a place you can visit. It's information preserved in the structure of the present. And the future. The future doesn't exist yet because it hasn't been determined. The universe is evolving from its current state toward higher entropy states, but which specific high entropy state it reaches depends on countless interactions that haven't happened yet. This is why the future feels open, because it is. The equations of physics are deterministic. If you know the exact state now, you can calculate the exact state later. But in practice, tiny uncertainties grow. Quantum mechanics adds true randomness. The future is genuinely unpredictable. But the past is fixed because it's encoded in the present. The information is still here. Low entropy structures preserve it. Now, here's something that should deeply bother you. If the laws of physics don't distinguish past from future, if time symmetry is fundamental, then the arrow of time is not a law. It's a condition, a contingent fact about our universe. In principle, there could be regions of the universe where entropy decreases. If some region happened to start in a high entropy state by chance, it would evolve toward lower entropy, and observers in that region would experience time running backward. Does this happen? Probably not anywhere large. The probability is too low. But in principle, it's possible. Small fluctuations, tiny pockets where entropy temporarily decreases could exist. In fact, this happens at small scales all the time. A few air molecules in a room might by chance momentarily cluster together, creating a temporary low entropy state. Then they spread out again. Entropy fluctuates. But for macroscopic systems, for anything big enough to contain observers, entropy only goes one direction, up. And that's the arrow of time, not a fundamental law, a statistical inevitability given the initial conditions. Think about the implications. Time doesn't flow because of some inherent property of time itself. Time is just a dimension, like space. You can move through it, in principle, in either direction. What we call the flow of time, the feeling that the present moment is moving from past to future, is a consequence of entropy increasing. It's a consequence of our brains being low entropy structures that form memories in the direction of entropy increase. If you could somehow reverse entropy, if you could make the universe spontaneously become more ordered, time would flow backward, the past would become the future, causes would follow effects, eggs would unscramble. But you can't, not on large scales. The statistics are too overwhelming. The number of high entropy states is too vast. Consider what this means for free will. Your decisions feel like they're shaping the future, and in a sense they are, but your decisions are physical processes in your brain, neurons firing, chemicals flowing, all following the laws of physics, all moving from lower entropy to higher entropy. Your sense of agency, your feeling that you're choosing the future, is itself a consequence of the arrow of time. You remember the past, you don't remember the future, so you feel like you're creating the future through your choices. But from the perspective of physics, your choices are just part of the causal chain, links between past and future, all constrained by entropy increase. This doesn't mean free will is an illusion. It means free will is a high-level description of a low-level physical process. Your choices are real. They have consequences, but they're embedded in the flow of entropy, like everything else. Here's another unsettling thought. If time's direction is determined by entropy, and entropy is about probability, then the arrow of time is statistical. It's not absolute. It's extremely likely, but not guaranteed. Imagine a small isolated system, a few dozen particles in a box. You start them in a high entropy state, randomly distributed. Most of the time, they'll stay high entropy. But occasionally, by pure chance, they might spontaneously arrange themselves into a lower entropy configuration. If you were a tiny observer living in that box, you would see time run backward during that fluctuation. Entropy would decrease. Broken things would assemble. Heat would flow from cold to hot. The arrow of time would reverse. This doesn't violate any laws. It's just extraordinarily unlikely for large systems. But for small systems, it can happen. Entropy can decrease by chance. Time's arrow can flicker. Now scale this up. Our entire observable universe is a system, a very large one. The probability of its entropy spontaneously decreasing is unimaginably small, so small that it will never happen before the heat death of the universe. But it's not impossible, just incredibly, ridiculously, absurdly improbable. This leads to a bizarre scenario called a Boltzmann brain. If you wait long enough in a high entropy universe, random fluctuations could spontaneously create a brain, complete with memories of a past that never happened. This brain would exist for a moment, then dissipate back into randomness. If the universe exists forever, Boltzmann brains become inevitable. Given infinite time, even the most improbable events happen. And a random brain fluctuating into existence is more probable than an entire universe with low entropy. This creates a strange problem. If Boltzmann brains are more common than real observers in ordered universes, then statistically you should be a Boltzmann brain. Your memories should be false, created by random fluctuation, not by actual past events. But you're probably not a Boltzmann brain. Probably. The fact that you're reading this, that the universe appears ordered, suggests you're a real observer in a real low entropy universe. But why? Why is the universe ordered rather than a random fluctuation? We're back to the same question. Why did the universe start with low entropy? No answer, just a mystery. The universe is heading toward maximum entropy, a state called heat death, where all energy is evenly distributed. No temperature differences, no structure, no stars, no galaxies, no gradients to drive processes. In that state, nothing happens. There's no arrow of time, because there's no change. The universe reaches equilibrium and stays there. How far away is this? Trillions of years. Maybe more. Stars will die. Black holes will evaporate. Eventually, everything will spread out and cool down. But even then, the laws of physics don't change. They're still time symmetric. What changes is entropy. And when entropy is maximum, there's no direction to time. So let's bring this together. Why does time only flow forward? Because the universe started in a low entropy state. That initial condition, combined with the statistical tendency for systems to evolve toward higher entropy, creates the arrow of time. The past is the direction of lower entropy. The future is the direction of higher entropy. And we, embedded in this flow, experience time moving from ordered past to disordered future. The fundamental laws don't impose this. They allow both directions. But the initial conditions of the universe, the low entropy Big Bang, set everything in motion. Why was the Big Bang low entropy? We don't know. That's the deepest mystery. But given that it was, everything else follows, the flow of time. The fact that we remember the past, but not the future. The fact that cause precedes effect. The fact that glasses break, but don't reassemble. All of it, every aspect of the direction of time, comes from one unexplained fact about the beginning of the universe. And that fact is not a law. It's a condition, an initial state, a boundary. Time is not a force. It's not a law. It's not a fundamental principle. Time is a consequence of how the universe began and how entropy behaves. The arrow of time is real. You feel it every moment. But it's not imposed by the fundamental structure of reality. It emerges from statistics, from probability, from the overwhelming likelihood that systems evolve from rare ordered states toward common disordered states. That's what time is. That's why it flows. That's why the past is fixed and the future is open. Not because of a law, because of an accident, a contingent fact, an unexplained beginning. And the fact that we can understand this, that we can see how the direction of time emerges from timeless laws and statistical mechanics, that's the beauty of physics. Not comfort, not certainty, truth.